Take a moment, just one moment. Close your eyes and think about where you are right now. You are sitting somewhere, maybe in your room, maybe on a couch, maybe in a cafe. You feel solid ground beneath you. You see walls around you. Everything feels contained, finite, and understandable. But now I want you to do something. I want you to zoom out. Imagine rising above your room, above your building, above your city. Keep going. Rise above your country, above the curved blue horizon of Earth. Now you are floating in the blackness of space, and Earth is a pale blue marble below you. Keep going. Fly past the moon, that silent gray companion that has watched over us for 4.5 billion years. Fly past Mars, that rusty red world where we dream of building a second home. Fly past Jupiter, a gas giant so massive that over 1,300 Earths could fit inside it, a world of raging storms and swirling clouds. Keep going. Fly past Saturn, with its breathtaking rings of ice and rock. Past Uranus and Neptune, those cold, distant ice giants at the edge of our solar system. Now you are in the Kuiper Belt, a region of frozen debris and dwarf planets, including tiny Pluto, which was once considered the 9th planet. Keep going. You pass through the Oort cloud, a vast spherical shell of icy objects that surrounds our entire solar system, stretching nearly halfway to the nearest star. And now you are truly in interstellar space. The sun behind you is just another star, one among billions. Keep flying. You cross the Milky Way galaxy, a barred spiral galaxy containing between 200 billion and 400 billion stars. Our sun is just one of them, located about 26,000 light-years from the galactic center. Now you leave the Milky Way behind. You fly past the Local Group, a collection of more than 50 galaxies held together by gravity. Past Andromeda, our nearest large galactic neighbor, which is on a collision course with the Milky Way, and will merge with us in about 4.5 billion years. Keep going. You fly past galaxy clusters and superclusters, vast cosmic structures containing thousands of galaxies each. You pass the Virgo supercluster, the Laniakea supercluster, structures so immense that light takes hundreds of millions of years to cross them. And still you keep going. Billions of galaxies stream past you, trillions of stars, quadrillions of planets. The numbers are so vast that the human mind cannot truly comprehend them. And then, after traveling billions upon billions of light-years, you approach something. A boundary, a limit, the farthest reaches of what we can observe, the edge of the observable universe. And here, right here, at this cosmic frontier, you stop. You float in the silence of deep space, surrounded by the faintest, most ancient light in existence. Light that has been traveling for almost 13.8 billion years to reach this point. And you look outward into the darkness beyond, and you ask the question that has haunted humanity since the very first person looked up at the night sky and wondered, what is out there? What lies beyond the edge? Is there a wall? Is there more space? Is there nothing? Is there everything? Is there something so alien, so incomprehensible that we have no words, no concepts, no mathematics to describe it? What really lies beyond the edge of the universe? This is not just a question. This is the question. It is the deepest, most profound, most terrifying, and most beautiful question that any conscious being can ask. It is a question that connects physics and philosophy, mathematics and metaphysics, science and spirituality. It is a question that the greatest minds in human history have wrestled with, from ancient Greek philosophers to modern theoretical physicists, from Aristotle to Einstein, from Copernicus to Hawking. And today, right now, in this very moment, we are going to explore this question together. We are going to go deeper than you have ever gone before. We are going to peel back layer after layer of reality, each one more mind-bending than the last. We are going to journey from the familiar to the absolutely unknown, from the things we can measure and observe to the things we can only theorize and dream about. And I promise you, by the end of this journey, the way you see the universe, the way you see reality, the way you see yourself, will never be the same again. Before we dive in, let me tell you what we are going to cover today, because this is going to be an epic journey. First, we need to understand what we even mean by the edge of the universe. This sounds simple, but it is far more complicated than you might think. We will explore the difference between the observable universe and the entire universe, a distinction that most people have never even heard of. Then, we will go back to the very beginning, to the Big Bang, and I will show you why the Big Bang is nothing like what most people imagine. We will explore the expansion of the universe and the terrifying discovery that the expansion is accelerating. We will dive into the shape of the universe, and yes, the universe has a shape, and that shape determines whether it has an edge or not. Then we will get to the main event, what actually lies beyond. We will explore 6 different possibilities, each one more extraordinary than the last. We will talk about the multiverse, about higher dimensions, about the possibility that we are living in a simulation, about mathematical structures that might be as real as the chair you are sitting on. We will explore the fate of the universe, how it will end, and what that means for the edge question. We will hear from the greatest physicists alive today. And finally, we will confront the most terrifying possibilities of all, ideas that keep cosmologists awake at night. So, if you love space, if you love deep questions, if you love having your mind completely and utterly blown, then you are in the right place. And if you find value in this kind of deep exploration, I need you to do something for me right now. Hit that like button. It takes half a second, it costs you nothing, but it tells the algorithm that this kind of content matters, that people want to think deeply, that people want to understand the cosmos. Subscribe to this channel if you have not already, and hit the bell so you never miss a video. And drop a comment right now before we even start. Tell me, what do you think lies beyond the edge of the universe? I want to know your intuition before we dive into the science, because your intuition might be closer to the truth than you think, or it might be completely, beautifully, wonderfully wrong. Now, let us begin. And let us start with something that sounds simple but is actually profoundly confusing. What do we mean by the edge of the universe? When most people hear the phrase, the edge of the universe, they imagine something like the edge of a map, a boundary, a line, a wall, maybe. On one side, there is stuff. Stars, galaxies, matter, energy, space. On the other side, there is something else, or nothing. Most people picture it like the edge of a room. Inside the room, there is furniture and air and light. Outside the room, there is either another room or the outdoors. The edge is the wall between them. But the universe is nothing like a room. The universe is not a container. The universe is not a box that stuff is inside of. The universe is everything. Space itself, time itself, matter, energy, the laws of physics, mathematics, logic, everything that exists in any sense of the word is part of the universe. So when we ask what is beyond the edge, we are not asking what is outside the box. We are asking what is beyond everything. And that is a fundamentally different kind of question. To make this even more confusing, we need to distinguish between 2 very different concepts that most people conflate: the observable universe and the entire universe. These are not the same thing, not even close. And understanding the difference is absolutely crucial for everything that follows. The observable universe is exactly what it sounds like. It is the portion of the universe that we can observe. It is the sphere of space around us from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. You might think that means we can see 13.8 billion light-years in every direction, but you would be wrong. Because of the expansion of space, the observable universe is actually about 93 billion light-years in diameter. We will talk about why later. For now, just know that the observable universe is a sphere about 93 billion light-years across, centered on us. Not because we are special, not because we are at the center of anything, but because it is the sphere of what we can see. An alien civilization in a galaxy a billion light-years away would have its own observable universe, the same size, centered on them. Their observable universe would overlap with ours, but would extend a billion light-years further in their direction, and a billion light-years less in the opposite direction. Every point in the universe has its own observable universe. Now, the observable universe is staggeringly large. It contains approximately 2 trillion galaxies. That is 2 million galaxies. Each of those galaxies contains anywhere from 100 million to 100 trillion stars. The total number of stars in the observable universe is estimated to be around 1 septillion. That is a 1 followed by 24 zeros, 10 to the power of 24. To put that in perspective, there are more stars in the observable universe than there are grains of sand on every beach and every desert on planet Earth. And each of those stars could have planets. The total number of planets in the observable universe might be in the tens of sextillions. The amount of matter in the observable universe is about 10 to the power of 80 atoms. That is a number so large that writing it out would take more digits than there are atoms in your body. But here's the thing. The observable universe, as incomprehensibly vast as it is, might be an inconceivably tiny fraction of the entire universe. The entire universe is everything that exists, not just what we can see. And the entire universe could be enormously, staggeringly, mind-breakingly larger than the observable universe. How much larger? Some estimates, based on measurements of the cosmic microwave background radiation by the Planck satellite, suggest that the entire universe is at least 250 times larger in diameter than the observable universe. But other estimates go much, much further. Some calculations based on inflation theory suggest the universe could be 10 to the power of 23 times larger than what we observe. That is a number so large that I cannot even give you a meaningful analogy. And some models predict that the universe is simply infinite, not just very large. Actually, literally infinite, going on forever in every direction. No edge, no boundary, no end. Just space and galaxies and stars, stretching outward without limit, forever and ever and ever. So when we ask what lies beyond the edge of the universe, we need to be very clear about what we mean. Are we asking what lies beyond the edge of the observable universe? Because that question has a relatively straightforward answer: more universe, more space, more galaxies, more stars. The observable universe is not a real boundary. It is just a limitation of our ability to see. It is like the horizon when you are standing on a hilltop. The horizon is the limit of your vision, but the world does not end at the horizon. There is more world beyond it. Similarly, there is more universe beyond the edge of our observable universe. We just cannot see it. But the deeper question, the one that really haunts us, is this: what lies beyond the edge of the entire universe? If the universe is finite, if it actually has a boundary, what is on the other side? And if the universe is infinite, what does that even mean? How can something be infinite? And is there anything beyond infinity? These are the questions we are going to tackle. And to do that, we need to start at the beginning, the very beginning, the moment everything started. The Big Bang. You have heard of it. Everyone has heard of it. It is one of the most famous scientific theories in history. But I can almost guarantee you that what you think the Big Bang was is wrong. Most people, when they think of the Big Bang, imagine something like this: a dark, empty void. Infinite darkness stretching in every direction. And then, in the center of this void, a tiny point of light appears. And then, boom! An enormous explosion, like the biggest bomb ever detonated, hurling matter and energy outward in every direction, filling up the previously empty space with stars and galaxies and planets. It is a dramatic picture. It is cinematic. It makes for great CGI. And it is almost entirely wrong. The Big Bang was not an explosion in space. The Big Bang was an explosion of space. This distinction is absolutely critical, and most people never understand it. Let me explain. In a normal explosion, like a bomb going off, you have matter being flung outward into a pre-existing space. There is a center point where the explosion starts, and material flies outward into the space that was already there. The space itself does not change. Only the stuff moving through it changes. The Big Bang was nothing like this. In the Big Bang, space itself was created. Space itself was born. There was no pre-existing void for the universe to expand into. There was no empty darkness waiting to be filled. Before the Big Bang, there was no space. There was no time. There was no before. The Big Bang created space, time, matter, and energy all at once. Everything that exists, the entire fabric of reality, came into being in that moment. This is incredibly hard to wrap your head around, and I want to be honest about that. Our brains did not evolve to understand these concepts. Our brains evolved to help us find food, avoid predators, and navigate the savannah. We think in terms of three-dimensional space and linear time because that is what we needed to survive. We intuitively understand concepts like inside and outside, and before and after, center and edge. But when we try to apply these intuitive concepts to the universe as a whole, they break down completely. Let me try to explain this with an analogy. Imagine a balloon. Not a deflated balloon, but one that is being inflated. Now, imagine that the entire universe is the surface of this balloon. Not the space inside the balloon, not the air, just the two-dimensional surface. Imagine that you are a tiny ant living on this surface. You can move forward and backward, left and right, but you have no concept of up or down because there is no third dimension accessible to you. Your entire universe is this two-dimensional surface. Now, imagine the balloon being inflated. The surface stretches. Every point on the surface moves away from every other point. If there were tiny dots drawn on the balloon representing galaxies, you would see them all moving apart from each other as the balloon expands. And here is the key. There is no center of expansion on the surface. No dot is at the center. Every dot sees every other dot moving away from it. Every dot thinks it is at the center of the expansion. But no dot is. The expansion is happening everywhere on the surface simultaneously. This is exactly what is happening in our universe, except in 3 dimensions instead of 2. Space itself is stretching, and every point in space is moving away from every other point. There is no center of the Big Bang. The Big Bang happened everywhere. It happened right where you are sitting. It happened on the moon. It happened in the Andromeda Galaxy. It happened at every single point in the universe simultaneously, because every single point in the universe was the Big Bang. The entire universe was compressed into an unimaginably small, unimaginably hot, unimaginably dense state, and then it expanded, and it is still expanding today. Now, there is one more piece of the Big Bang story that is absolutely crucial for our question, and that is inflation. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. The universe underwent a period of mind-bogglingly rapid expansion called cosmic inflation. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in a time span of about 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds. Let me put that in perspective. In less than a billionth of a trillionth of a trillionth of a second, the universe went from being smaller than a proton to being larger than the entire observable universe is today. The universe expanded faster than the speed of light during inflation. How is that possible? Remember, the speed of light is the maximum speed at which anything can travel through space, but there is no speed limit on the expansion of space itself. Space can stretch as fast as it wants. Inflation was proposed in 1980 by physicist Alan Guth, and it solved several major problems with the original Big Bang theory. It explained why the universe is so uniform in every direction. It explained why the geometry of the universe is so flat. It explained where the initial quantum fluctuations came from that eventually grew into galaxies and galaxy clusters. And it is supported by evidence from the cosmic microwave background radiation. But inflation also introduced something deeply unsettling. It suggested that the universe is far, far larger than what we can observe. The observable universe might be an inconceivably tiny patch of a much, much larger cosmos, and depending on the details of how inflation worked, inflation might be eternal. It might still be happening in most of the universe, spawning new regions of space, new pocket universes, each with potentially different properties. But we will get to that later. For now, just hold on to this. The Big Bang was not an explosion in space. It was the birth of space, and inflation made the universe enormously larger than what we can see. Now, let us talk about something that was one of the most important discoveries in the history of science, a discovery that completely changed our understanding of the cosmos, and that has profound implications for what lies beyond the edge. Let us talk about the expansion of the universe. In 1929, an astronomer named Edwin Hubble made a revolutionary observation. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble measured the distances and velocities of a number of galaxies. What he found shocked the world. Almost every galaxy he observed was moving away from us. Not just a few galaxies, almost all of them. And there was a pattern. The farther away a galaxy was, the faster it was receding from us. This relationship, now known as Hubble's law, was the first direct evidence that the universe is expanding. It was not static, it was not eternal and unchanging, it was growing. This discovery was so groundbreaking that even Einstein, whose own equations had predicted the possibility of an expanding universe, had refused to believe it. Einstein had introduced a cosmological constant into his equations specifically to prevent them from predicting expansion, because the prevailing belief at the time was that the universe was static. When Hubble's observations proved that the universe was expanding, Einstein called his cosmological constant the biggest blunder of my life. Although, in a delicious twist of cosmic irony, the cosmological constant would later be resurrected in a completely different context, as we will see. Hubble's discovery meant that if you ran the clock backward, if you traced the expansion in reverse, the universe must have been smaller in the past. And the further back you go, the smaller and denser and hotter the universe was. Run the clock all the way back, and you arrive at a singularity, a point of infinite density and infinite temperature. This was the birth of the Big Bang theory, the idea that the universe had a beginning, that it started in an incredibly hot, dense state, and has been expanding and cooling ever since. But the story did not end there. In 1998, two independent teams of astronomers made a discovery that shocked the scientific community even more than Hubble's original finding. They were studying a particular type of exploding star called a Type 1a supernova. These supernovae are useful because they all have roughly the same intrinsic brightness, so by measuring how bright they appear to us, we can figure out how far away they are. The teams expected to find that the expansion of the universe was slowing down. After all, gravity pulls matter together, and you would expect the mutual gravitational attraction of all the matter in the universe to gradually slow the expansion, like a ball thrown upward, gradually slowing before it falls back down. But that is not what they found. They found the opposite. The expansion of the universe is not slowing down, it is speeding up. The universe is expanding faster and faster with every passing moment. This was such a shocking and unexpected result that the two teams initially thought they had made a mistake. They checked and rechecked their data, but the result held up. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery. But what could be causing the expansion to accelerate? Gravity pulls things together. What force could be pushing things apart so powerfully that it overwhelms the gravitational attraction of all the matter in the entire universe? Scientists gave this mysterious force a name: dark energy. And dark energy is, without exaggeration, the deepest mystery in all of physics. We know almost nothing about dark energy. We cannot see it. We cannot detect it directly. We cannot create it in a laboratory. We have no idea what it actually is, but we know it is there because we can see its effects. And those effects are staggering. Dark energy makes up approximately 68% of the total energy content of the universe. Let me repeat that, 68%. The ordinary matter that makes up everything you can see, every star, every planet, every person, every atom of every element in the periodic table, makes up only about 5% of the universe. Another 27% is dark matter, a mysterious substance that we can detect through its gravitational effects, but that does not interact with light. And the remaining 68% is dark energy. We are made of the minority ingredient. The universe is mostly made of stuff we do not understand at all. Dark energy behaves in a way that is deeply counterintuitive. Unlike matter and radiation, which become more dilute as the universe expands, dark energy appears to have a constant density. As space expands and the volume of the universe increases, the total amount of dark energy increases too, because there is the same amount of dark energy per unit volume, but more volume. This means that as the universe gets bigger, there is more and more dark energy, which pushes the expansion faster, which creates more space, which creates more dark energy, which pushes the expansion even faster. It is a runaway process, an accelerating expansion that only gets faster and faster. The implications of this for our question about the edge of the universe are profound and, frankly, terrifying. Because of the accelerating expansion, galaxies that are far enough away from us are being carried away faster than the speed of light. Remember, there is no speed limit on the expansion of space itself. Only movement through space is limited to the speed of light. Space can expand faster than light. And this means that light from those distant galaxies will never, ever reach us. They are beyond our event horizon. They are lost to us forever. And it gets worse. As the expansion continues to accelerate, more and more galaxies will cross this event horizon. They will be carried away beyond the point where we can ever see them, ever communicate with them, ever know anything about them. The observable universe is shrinking, in a sense. We are being cut off from more and more of the cosmos with every passing moment. Eventually, in the far, far future, billions upon billions of years from now, intelligent beings in our galaxy will look out into the sky and see nothing. No other galaxies, just empty black void. They will think they are alone. They will think their galaxy is the entire universe, and they will have no way of knowing that there was ever anything else out there. All the evidence will have been carried away beyond the horizon. This is one of the most haunting facts in all of science. We live at a special time, a time when we can still see the evidence of the Big Bang, the evidence of cosmic expansion, the evidence of billions of galaxies. Future civilizations will have none of this. The universe is slowly, inexorably, pulling a curtain across itself. And once that curtain is drawn, it can never be opened again. But this raises a fascinating point. If the accelerating expansion is carrying galaxies beyond our horizon, then there is definitely something beyond the edge of the observable universe. More galaxies, more space, more universe. The edge of the observable universe is not a real boundary. It is just the limit of what we can see. And what lies beyond it, at least in the near vicinity, is simply more of the same. More galaxies, more stars, more planets, more empty space. The edge of the observable universe is like the horizon on the open ocean. You cannot see past it, but there is definitely more ocean out there. The real question, the one that gets to the heart of what we are discussing today, is not about the observable universe. It is about the entire universe. Does the entire universe have an edge? And if so, what is beyond it? And to answer that, we need to talk about something truly mind-bending. The shape of the universe. When I say the shape of the universe, I am not talking about what the universe looks like from the outside, because there may be no outside to look from. I am talking about the geometry of space itself. And this geometry is not just an abstract mathematical curiosity. It determines the ultimate fate of the universe, whether the universe is finite or infinite, and whether it has an edge or not. According to Einstein's theory of general relativity, the curvature of space is determined by the amount of matter and energy within it. Massive objects like stars and black holes curve space around them, and this curvature is what we experience as gravity. But on the largest scales, the overall curvature of the universe as a whole depends on the total density of all the matter and energy in the universe. This total density is compared to a critical value called the critical density, and the ratio is denoted by the Greek letter omega. If omega is exactly equal to 1, the universe is flat. If omega is greater than 1, the universe has positive curvature. If omega is less than 1, the universe has negative curvature. And each of these possibilities leads to a profoundly different universe. Let us start with the first possibility: positive curvature, also known as a closed universe. If the density of the universe is greater than the critical density, then space curves back on itself, like the surface of a sphere. Imagine, once again, the surface of a balloon. This is a two-dimensional surface that is curved and finite, but it has no edge. An ant walking on the surface of a balloon can walk in any direction forever, without ever reaching an edge or a boundary. But the surface is still finite. It has a definite, measurable area. The ant, if it walked in a straight line long enough, would eventually come back to where it started, having circumnavigated the entire surface. A closed universe would be the three-dimensional analog of this. It would be a finite volume of space, but with no edges and no boundaries. You could fly in a straight line in a spaceship, and if you flew long enough, you would eventually return to your starting point, having circumnavigated the entire universe. You would never encounter a wall or an edge. The universe would just seamlessly curve back on itself. In fact, in a closed universe, If you looked far enough with a sufficiently powerful telescope, you would eventually see the back of your own head, because the light you emitted would travel all the way around the universe and come back to you. Of course, this assumes the universe is small enough and long-lived enough for light to make the complete journey, which it probably is not. But the principle is fascinating. Einstein was fond of this model. He liked the elegance of a universe that was finite yet had no boundary, a universe that was complete and self-contained. But observations have not been kind to this model. Most measurements, particularly those from the Wilkinson Microwave Anisotropy Probe, known as WMAP, and the Planck satellite, suggest that the universe is flat, not positively curved. However, and this is important, these measurements have a margin of error. The universe could have a very slight positive curvature that is too small for us to detect with our current instruments. A few research papers have even suggested that the data shows a slight preference for positive curvature, though this remains controversial, and most cosmologists consider the evidence inconclusive. There is also an intriguing possibility within the closed universe model called the Poincaré dodecahedral space. This is a model proposed by Jean-Pierre Luminet and colleagues in 2003, which suggests that the universe might have the shape of a dodecahedron, a 12-sided polyhedron. In this model, opposite faces of the dodecahedron are identified with each other, meaning that if you flew through one face, you would emerge from the opposite face, like in a video game. The universe would be finite, relatively small, and would produce specific patterns in the cosmic microwave background radiation. Some researchers have claimed to see these patterns, but the evidence is not conclusive. Now, let us consider the second possibility, negative curvature, also known as an open universe. If the density of the universe is less than the critical density, then space has a saddle-like curvature, like the surface of a Pringle chip or a horse saddle. In 2 dimensions, this kind of surface curves in opposite directions. If you are sitting at the center of a saddle, the surface curves upward in front and behind you, but downward to your left and right. In a negatively curved space, the rules of geometry are different from what we are used to. Parallel lines diverge from each other. The angles of a triangle add up to less than 180 degrees. Circles have more area than you would expect based on their circumference. An open universe would be infinite in extent. It would stretch on forever in every direction. There would be no edge, no boundary, because infinity has no edge. You could travel in a straight line forever and never reach the end of space. This universe would also expand forever, the expansion never stopping, the galaxies getting farther and farther apart for all eternity. And then there is the third possibility, and this is the one that the evidence points to, a flat universe. If the density of the universe is exactly equal to the critical density, then space is flat. Not flat in the sense of being two-dimensional, but flat in the sense that the rules of ordinary Euclidean geometry apply on large scales. Parallel lines remain parallel. The angles of a triangle add up to exactly 180 degrees. Circles have exactly the area you would expect. All of our best measurements from WMAP, from Planck, from observations of Type 1a supernovae, from the large-scale distribution of galaxies, consistently point to the same conclusion. The universe is flat. More precisely, the universe is flat to within a margin of error of about 0.5%. Omega is equal to 1, plus or minus about 0.004. This is an astonishing result. Out of all the possible curvatures the universe could have, it apparently has no curvature at all, or as close to no curvature as we can possibly measure. This seems like an incredible coincidence, and in a sense it is. If the density of the early universe had been different by even 1 part in 10 to the power of 60, the universe would not be flat today. It would be either wildly curved and collapsed, or wildly curved and so diffuse that galaxies could never have formed. The fact that it is so precisely flat demands an explanation, and that explanation is, once again, inflation. Inflation theory predicts that no matter what the initial curvature of the universe was, the rapid expansion during inflation would have stretched space so much that any curvature would be flattened out, just as the surface of a balloon becomes flatter and flatter as you inflate it. If you stand on a balloon that is the size of Earth, the surface looks flat to you, even though it is actually curved. Inflation made the universe so immense that any curvature is undetectable on the scale of the observable universe. But here is where things get really interesting. A flat universe could be either infinite or finite. Most people assume that if the universe is flat, it must be infinite, but that is not necessarily true. The flatness of the universe tells us about its local geometry, the curvature at any particular point. But it does not tell us about its global topology, its overall shape and connectivity. Topology is different from geometry. Geometry tells you about curvature and angles and distances. Topology tells you about the overall shape and how different parts of a space are connected to each other. Let me give you an example. Take a flat sheet of paper. It is flat, it has zero curvature. Now roll it into a cylinder. It is still flat, still has zero curvature, at least intrinsically. The angles of triangles drawn on it still add up to 180 degrees, but its topology has changed. Instead of being an infinite flat plane, it is now a cylinder, a shape that is finite in one direction and infinite in the other. Now take that cylinder and bend it into a donut shape, a torus. It is still intrinsically flat, but now it is finite in all directions. You can walk in any direction and eventually return to where you started. A flat torus has zero curvature but finite volume. No edge, no boundary, but finite. The universe could be like this. It could be flat, with zero curvature on large scales, but still have a finite volume due to its topology. It could be a three-dimensional torus, wrapping around in all three spatial dimensions. In such a universe, if you flew far enough in any direction, you would eventually come back to where you started. Like a character in the video game Pac-Man, going off one side of the screen and appearing on the other. Scientists have actually searched for evidence of such topology in the cosmic microwave background radiation, looking for repeating patterns or matching circles that would indicate a universe that wraps around on itself. So far, no conclusive evidence has been found, but the search continues. Other exotic topologies are possible too. The Klein bottle, a surface that is flat but has only one side, like a Mobius strip but in higher dimensions. The real projective plane, the three-sphere. These are mathematical objects that are hard to visualize but perfectly well defined. The universe could have any of these topologies. The key takeaway from all of this is that the question of whether the universe has an edge is intimately tied to its geometry and topology. If the universe is positively curved and closed, it has no edge but is finite. You can circumnavigate it. If the universe is negatively curved and open, or flat and infinite, it has no edge and stretches on forever. If the universe is flat but has a compact topology, it has no edge but is finite and wraps around on itself. In none of these cases does the universe have an edge in the traditional sense. There is no wall, no boundary, no place where space ends and something else begins. But wait, that cannot be the whole story. Because even if the universe has no edge, even if it is infinite, there is still the question of what it is inside. If the universe is a bubble of space, what is the bubble floating in? If the universe is the surface of a higher dimensional sphere, what is the sphere embedded in? these questions lead us to some of the most extraordinary ideas in all of physics. And this is where we get to the heart of what really lies beyond the edge. Let me take you through 6 possibilities. 6 answers to the question of what lies beyond. Each one is a serious scientific proposal, backed by mathematical reasoning and, in some cases, empirical evidence. Some are widely accepted by the scientific community. Others are more speculative. But all of them are mind-blowing. The first possibility is the simplest, and, many physicists would argue, the most likely. Beyond the edge of the observable universe lies simply more universe. More space, more galaxies, more stars, more empty void. The observable universe is not the whole universe. It is a tiny bubble of visibility within a much larger cosmos. The entire universe may be enormously larger than the observable universe, possibly infinitely larger. And what is out there, beyond our cosmic horizon, is probably just more of the same. The same laws of physics, the same types of particles, the same kinds of galaxies. This is what inflation theory predicts. During inflation, the universe expanded so rapidly and so uniformly that any region of the universe should look pretty much like any other region. The part of the universe we can see is a representative sample of the whole, like a teaspoon of ocean water that tells you the salinity of the entire ocean. This seems like the boring answer, I know. More of the same. How anticlimactic. But let me tell you why this answer is actually terrifying. Because if the universe is truly infinite, then something extraordinary follows from pure mathematics. In an infinite universe, every possible arrangement of particles is realized somewhere. Let me explain what I mean. The observable universe contains a finite number of particles, roughly 10 to the power of 80. These particles can be arranged in a finite number of ways. The number of possible arrangements is enormous, but it is finite. It is something like 10 to the power of 10 to the power of 122. That is a number so large that writing it out in standard notation would require more digits than there are particles in the observable universe. But it is finite. And in an infinite universe, there are infinitely many regions the size of our observable universe. If each of those regions has a random arrangement of particles, and there are only a finite number of possible arrangements, then eventually arrangements must repeat. This means that in an infinite universe there is another region of space, inconceivably far away, that contains an exact copy of the observable universe. An exact copy. With an exact copy of the Milky Way galaxy, and an exact copy of the solar system, and an exact copy of Earth, and an exact copy of you. Sitting in the same room, reading the same words, having the same thoughts. There would be infinitely many such copies, in fact. And there would be infinitely many near copies, too. Versions of you that are identical except for one atom in your left thumbnail. Versions of you that are identical except they chose a different career. Versions of Earth where the dinosaurs never went extinct. Versions where the Roman Empire never fell. Versions where humans evolved with 8 limbs. Versions where the laws of physics produced a world recognizable to us but subtly different in ways we cannot predict. This is not science fiction. This is not fantasy. This is a mathematical consequence of an infinite universe with finite possible configurations. It is taken seriously by mainstream physicists. Max Tegmark of MIT calls this the Level 1 multiverse. The idea that an infinite universe necessarily contains all possible histories and all possible arrangements of matter, repeated infinitely many times. The distance to the nearest exact copy of our observable universe would be staggering. Tegmark has estimated it at roughly 10 to the power of 10 to the power of 118 meters. That number is so inconceivably large that there is no way to convey it through analogy. It is not just larger than the observable universe. It is larger than the observable universe raised to the power of the observable universe raised to the power of the observable universe, repeated more times than there are particles in the universe. It is a distance that makes infinity feel small. But in a truly infinite universe, that distance is nothing. There is always more space, always more room, always more copies. And this brings us to a deeply philosophical point. If there are infinite copies of you, are they really you? Are you unique? Or are you just one instance of a pattern that repeats infinitely across the cosmos? What does identity even mean in an infinite universe? Think about it this way. Right now, an exact copy of you, an identical copy down to every last atom, is having this exact same experience in a region of the universe so far away that you could never reach it, never communicate with it, never even know it exists. That other you is just as real as you are. They have the same memories, the same personality, the same sense of being uniquely themselves. And from their perspective, you are the copy. Who is the real one? The answer, of course, is that they are both equally real. Neither is a copy, both are original, both are genuine. The concept of uniqueness breaks down in an infinite universe. And this is not even the most radical possibility. The second possibility is that the universe has a literal, physical edge, a boundary where space itself ends. This might seem like the most intuitive answer. After all, everything we know has an edge. Your room has walls, your city has borders, your planet has a surface. Your solar system has a boundary. Why should not the universe? But think about this carefully. What would such an edge look like? What would happen if you reached it? This thought experiment was first proposed by the ancient Greek philosopher Archytas of Tarentum, a contemporary of Plato, more than 2,400 years ago. Archytas imagined standing at the supposed edge of the universe and extending his hand, or a stick, beyond it. Two things could happen. Either the stick passes through the edge, in which case the edge is not really the edge, because there is space on the other side for the stick to extend into. Or the stick is blocked by something, but then what is blocking it? Whatever is blocking the stick, a wall, a barrier, a force field, that thing must exist in space. And if it exists in space, then there is space beyond the supposed edge, and it is not really the edge. Archytas argued that this reasoning could be repeated infinitely, so the universe could not have an edge. It must be infinite. This is a clever argument, but it has a hidden assumption, that the concept of beyond always makes sense, and that assumption might be wrong. Consider the surface of Earth. If you are an ant walking on the surface and you keep walking in one direction, you never reach an edge. The surface has no edge. But it is not infinite either. The ant just goes around and around. The question, what is beyond the edge of the Earth's surface, does not make sense, because there is no edge to be beyond. Similarly, the question, what is beyond the edge of the universe, might not make sense if the universe has no edge. The question itself might be malformed, like asking, what is north of the North Pole? The North Pole is the northernmost point on Earth. There is nothing north of it. Not because there is a wall or a barrier, but because north simply does not apply anymore. You have reached the end of the concept, not the end of space. This is, in fact, the position taken by Stephen Hawking. In his famous no-boundary proposal, developed with James Hartley in the 1980s, Hawking suggested that the universe has no boundary in space or in time. Near the Big Bang, time itself becomes indistinguishable from space. The question, what happened before the Big Bang, is like asking, what is south of the South Pole? It is a question that seems meaningful but actually is not, because the concept of before loses its meaning when time itself does not exist. Similarly, the question, what is beyond the edge of the universe, might be a question without meaning if the universe has no edge for something to be beyond. But let me play devil's advocate for a moment. What if the universe does have a literal edge? What if space just stops? Some speculative models in physics allow for this possibility. In these models, the edge of the universe would not be a wall. It would be something far stranger. It might be a region where the laws of physics themselves break down. The fundamental constants might change. The forces of nature might transform. Space and time might unravel. Beyond this edge, there would not be nothing, in the way we usually think of nothing, meaning empty space. There would be the absence of space itself. No dimensions, no distance, no time, no physics, no mathematics. True, absolute, total nothingness. Not darkness, because darkness is something, it is the absence of light in a space that exists. Not emptiness, because emptiness is something, it is a volume with nothing in it. This would be the absence of volume itself, the absence of existence, a state so alien to our experience that we literally cannot conceive of it. Our brains are not equipped to think about the absence of everything, because even when we try to imagine nothing, we imagine a black void, and a black void is still something. So the second possibility, while intellectually interesting, is probably incoherent. Most physicists believe that the universe does not have a literal edge, but if it does, what lies beyond is not anything we can describe or comprehend. The third possibility is, to me, the most extraordinary and thrilling of all. Beyond the edge of our universe might be other universes. Not just more space, not just nothing, but entire separate realities, each with their own space, their own time, their own physics, their own history. This is the multiverse. The multiverse is not a single theory. It is a collection of ideas that have emerged independently from several different areas of physics. The fact that multiple unrelated lines of reasoning all point to the existence of other universes has struck many physicists as remarkable and suggestive, though not everyone is convinced. Let me walk you through the most important multiverse theories. The first and most widely discussed version is the bubble universe model, also known as the inflationary multiverse or eternal inflation. This idea emerges naturally from the theory of cosmic inflation that we discussed earlier. Remember, inflation was the period of extremely rapid expansion in the very early universe. Inflation was driven by a quantum field called the inflaton field, which was in a high-energy state called a false vacuum. As the inflaton field decayed from its high-energy state to a low-energy state, the energy released drove the expansion of space. In our observable universe, inflation ended about 10 to the power of negative 32 seconds after the Big Bang. The inflaton field decayed, inflation stopped, and the universe transitioned to the slower expansion we observe today. But here is the crucial insight, first articulated by physicists like Andrei Linde, Alexander Vilenkin, and Alan Guth. Even though inflation ended in our region of the universe, it may not have ended everywhere. In some regions of the universe, the inflaton field may not have decayed yet. Those regions are still inflating, still expanding at an exponential rate. And within those still inflating regions, other pockets might occasionally decay, just as ours did, creating other bubble universes. Each bubble universe undergoes its own Big Bang, its own inflation, its own cosmic history. And the bubbles are being carried apart by the still inflating space between them at a rate far exceeding the speed of light. They can never interact. They can never communicate. They are, for all practical purposes, completely separate universes. Eternal inflation predicts not just a few bubble universes, but an infinite number of them. The inflating space, which is called the multiverse or the inflationary multiverse, goes on forever, constantly spawning new bubble universes. Our universe is just one bubble in an infinite, ever-expanding, ever-spawning foam of universes. And each bubble universe might have different properties. The fundamental constants of nature, the masses of particles, the strengths of forces, might vary from bubble to bubble. This is because the specific values of these constants depend on how the inflaton field decayed, and different bubbles might experience different decay pathways. Some bubbles might have a strong nuclear force that is slightly stronger than ours, leading to a universe where hydrogen cannot exist, and life as we know it is impossible. Other bubbles might have a cosmological constant that is enormous, causing space to expand so rapidly that atoms are ripped apart before they can form. Others might have extra dimensions of space. Others might have completely different particles and forces, governed by physics that we cannot even imagine. This connects to string theory, which predicts the existence of a vast landscape of possible physical laws. String theory is a framework that attempts to unify all the forces of nature, including gravity, into a single, coherent theory. In string theory, the fundamental constituents of the universe are not point particles, but tiny vibrating strings of energy. The way these strings vibrate determines the properties of the particles they produce. And the way the strings vibrate depends on the geometry of the extra dimensions predicted by string theory, 6 or 7 extra dimensions of space that are curled up so small that we cannot detect them. The number of possible geometries for these extra dimensions is estimated to be around 10 to the power of 500. That is a number with 500 zeros. Each geometry corresponds to a different set of physical laws, a different vacuum in the string landscape. And if eternal inflation is real, then each of these 10 to the power of 500 possible vacua might be realized in some bubble universe somewhere. Every possible set of physical laws that is consistent with the mathematics of string theory exists as a real physical universe somewhere in the multiverse. This is a staggering idea. It means that the universe we observe, with its specific particles and forces and constants, is not special. It is not the only way a universe can be. It is just one possibility out of an inconceivable number. And beyond the edge of our universe, beyond our bubble, lies an infinite ocean of other bubbles, each one a complete universe, each one potentially hosting its own version of physics, its own version of chemistry, its own version of complexity, maybe even its own version of life. Life that would be unrecognizable to us. Life built from particles and forces that do not exist in our universe. Life that thinks and dreams and wonders and asks its own version of the question, what lies beyond the edge? Now, I need to be honest with you. The multiverse is not universally accepted in the scientific community. Some physicists embrace it as a natural consequence of well-established theories like inflation and string theory. Others are deeply skeptical. The main criticism is that the multiverse might be unfalsifiable. If other universes can never interact with ours, if we can never detect them or gather evidence for their existence, then is the multiverse really a scientific theory? Or is it more like philosophy, or even faith? Science is supposed to make testable predictions. If a theory cannot be tested, even in principle, is it really science? This is a legitimate concern, and it is the subject of intense debate. But it is worth noting that the multiverse does make some indirect predictions. For example, eternal inflation predicts specific patterns in the cosmic microwave background radiation. If our bubble universe collided with another bubble universe in the past, it would leave a distinctive circular bruise in the CMB. Several teams have searched for such signatures, and while some have claimed tentative detections, the evidence is not yet conclusive. Additionally, the multiverse provides an explanation for the apparent fine-tuning of the universe for life, a topic we will discuss shortly. I want to pause here and ask you to think about something. We are now deep in the heart of this journey, and we have covered some incredibly profound territory. We have talked about the observable universe, the expansion of space, the shape of the cosmos, and the possibility that our universe is just one bubble in an infinite foam of universes. If you are finding value in this exploration, I want to ask you to do something. Share this video with someone who would appreciate it. A friend, a family member, a colleague who loves to think deeply about the nature of reality. And if you are not subscribed, this is the perfect moment to subscribe, because we are about to go even deeper. The fourth possibility for what lies beyond the edge of the universe takes us into even more exotic territory. It involves higher dimensions of space beyond the three that we experience in our everyday lives. This idea comes from several areas of theoretical physics, including string theory and a framework known as brain-world cosmology. Let me explain. In our everyday experience, space has three dimensions: length, width, and height, up and down, left and right, forward and backward. We can move freely in all three of these dimensions. Time is sometimes considered a fourth dimension, but it is fundamentally different from the spatial dimensions. We move through time in only one direction and cannot control our movement. But some theories of physics predict that there are additional spatial dimensions beyond the three we know. String theory, for example, requires either 10 or 11 dimensions of spacetime for its mathematics to be consistent. Since we only observe 4 dimensions, 3 of space and 1 of time, the extra dimensions must be hidden somehow. There are 2 main proposals for how they are hidden. The first is that the extra dimensions are compactified, meaning they are curled up so incredibly small that we cannot detect them. Imagine an ant on a very thin wire. From far away, the wire looks like a one-dimensional line. But up close, the ant can move around the circumference of the wire, revealing a second dimension that was too small to see from a distance. Similarly, the extra dimensions of string theory might be curled up at scales of about 10 to the power of -35 meters, the Planck length, far too small for any conceivable experiment to detect. But the second possibility is more relevant to our question. In the brain-world scenario proposed by physicists like Lisa Randall and Raymond Sundrum, the extra dimensions are not necessarily small. They might be large, possibly even infinite. In this model, our three-dimensional universe is a brane, short for membrane, floating in a higher dimensional space called the bulk. Think of it like a sheet of paper floating in a room. The paper is a two-dimensional surface, and the room is a three-dimensional space. Creatures living on the paper would experience only 2 dimensions, even though they are embedded in a three-dimensional space. Similarly, we might be three-dimensional creatures living on a three-dimensional brain, embedded in a higher dimensional bulk that we cannot perceive. In the brain-world scenario, all the particles and forces of the standard model, photons, electrons, quarks, the strong force, the weak force, electromagnetism, are confined to our brain. They cannot leave the brain and venture out into the bulk. This is why we do not perceive the extra dimensions. Our matter and our light are stuck on the brain. However, gravity might be different. Some versions of the brain world model predict that gravity, unlike other forces, can leak into the bulk. This could explain why gravity is so much weaker than the other forces of nature. The electromagnetic force, for example, is about 10 to the power of 36 times stronger than gravity. This seems like an odd imbalance, and the brain world model offers a potential explanation. Gravity is weak because it is spread out across the extra dimensions, while the other forces are concentrated on our brain. Now, if the brain world scenario is correct, then the answer to what lies beyond the edge of the universe is breathtaking. Beyond our brain, in the bulk, there might be other brains, other three-dimensional universes, floating in the higher dimensional space, possibly very close to us in the extra dimension. Imagine two sheets of paper, each representing a separate universe, hovering parallel to each other with only a tiny gap between them. The inhabitants of each sheet would be completely unaware of the other sheet. They would perceive only their own two-dimensional world. But the two sheets would be separated by only a millimeter, a centimeter, a fraction of an inch in the dimension they cannot access. Similarly, another universe, a completely separate reality with its own matter, its own galaxies, its own stars, its own planets, maybe even its own life, could be hovering just millimeters away from us in a higher dimension. We would have no way of reaching it, no way of seeing it, no way of knowing it is there, because we are trapped on our brain. The only hint of its existence might come through gravity, the one force that can leak between brains. Some physicists have even speculated that dark matter, the mysterious substance that makes up 27% of the universe but cannot be seen, might actually be ordinary matter on a nearby brain. Its gravity leaks across the dimensional gap and affects our brain, but its light and other properties are confined to the other brain, making it invisible to us. There is an even more dramatic version of this scenario called the ekpyrotic model, proposed by Paul Steinhardt, Neil Turok, and others. In this model, the Big Bang was not the beginning of everything. It was a collision between two brains. Picture two parallel sheets drifting slowly toward each other in the bulk. When they collide, the energy of the collision is converted into matter and radiation on each brain. This collision is the Big Bang. Each brain experiences a Big Bang simultaneously, each one giving birth to a universe of matter and energy. After the collision, the brains bounce apart, drift for a while, and then are drawn together again by a force, colliding again and producing another Big Bang. In this model, the universe is cyclic, undergoing an endless series of Big Bangs and expansions, each one triggered by a brain collision. There is no beginning and no end, just an eternal cycle of creation and expansion and collision and recreation. If this model is correct, then beyond the edge of our universe, in a higher dimension, might be the brain that gave birth to us through a cosmic collision billions of years ago. And that brain might be drifting slowly toward us right now, inching closer and closer, in a dimension we cannot perceive, eventually destined to collide with us again and trigger a new Big Bang, a new beginning, a new universe born from the ashes of the old. The fifth possibility is perhaps the most philosophically unsettling of all. It is the idea that there is nothing beyond the edge of the universe because the universe is a simulation, and the edge is where the simulation stops rendering. The simulation hypothesis, most famously articulated by philosopher Nick Bostrom in 2003, begins with a seemingly simple argument. If it is possible for a sufficiently advanced civilization to create a computer simulation of a universe that is realistic enough that the simulated beings within it believe they are real, then such simulations are likely to be created. And if they are created, they are likely to be created in vast numbers, because running a simulation for an advanced civilization would be trivial. And if there are vastly more simulated universes than real ones, then any given conscious being is statistically far more likely to be in a simulation than in the base reality. This argument is deceptively simple but remarkably difficult to refute. and it has some interesting connections to physics. In quantum mechanics, particles do not have definite properties until they are observed or measured. Before measurement, a particle exists in a superposition of all possible states. It is only when you look at it that it chooses a state. This is remarkably similar to how a video game works. In a video game, the computer does not render the entire game world at all times. It only renders the parts that the player is looking at. The rest of the world does not exist in a fully detailed state until the player turns to look at it. Could quantum mechanics be the universe's version of this optimization? Could the universe only be rendering what is being observed to save computational resources? Moreover, there are fundamental limits on the resolution of the universe. The Planck length, about 10 to the power of negative 35 meters, appears to be the smallest meaningful distance. The Planck time, about 10 to the power of negative 43 seconds, appears to be the smallest meaningful interval of time. You cannot have a distance smaller than the Planck length or a time shorter than the Planck time. These are not just practical limits, they seem to be fundamental. It is as if the universe has a finite resolution, like the pixels on a screen. Could this be because the universe is a simulation, and the Planck scale is the pixel size? Now, I want to be clear, the simulation hypothesis is not mainstream science. It is more of a philosophical thought experiment, and it has significant problems. For one, it leads to an infinite regress. If our universe is a simulation, what about the universe that is running the simulation? Is that a simulation too? And the universe running that simulation? It is turtles all the way down. For another, the hypothesis is extremely difficult, maybe impossible, to test. How could you ever prove you are in a simulation? Some physicists, like Silas Bean, have suggested looking for artifacts in the cosmic ray spectrum that might indicate a lattice structure to spacetime, which would be expected if the universe were simulated on a discrete grid. But such tests are highly speculative. If the simulation hypothesis is true, then what lies beyond the edge of the universe is the computational substrate on which the simulation is running. Perhaps a vast quantum computer in the base reality. The edge of the universe would be the edge of the simulation, the point beyond which the program does not generate data. And beyond that edge would be the real world, whatever that might be. A world that could be utterly different from ours. A world with different dimensions, different physics, different rules. A world that might bear no resemblance whatsoever to the virtual world we inhabit. The sixth and final possibility I want to discuss is the most abstract and the most philosophically radical. It is the idea that beyond the edge of the universe lies the realm of pure mathematics. This is the mathematical universe hypothesis, proposed by physicist Max Tegmark of MIT. Tegmark argues that the universe does not merely follow mathematical laws. The universe is a mathematical structure. Mathematics is not just a language we use to describe reality. It is reality. And every self-consistent mathematical structure is not just abstractly real, but physically real. Every possible universe that can be described by mathematics exists, just as concretely and tangibly as ours. This is an extraordinary claim, so let me unpack it. Think about what it means for the universe to be governed by mathematical laws. The equations of physics, like Newton's law of gravitation, or Maxwell's equations of electromagnetism, or Einstein's field equations of general relativity, or Schrödinger's equation of quantum mechanics, these equations describe how the universe behaves with extraordinary precision. The predictions of these equations have been confirmed to dozens of decimal places. The universe obeys mathematics with a fidelity that borders on the miraculous. Why? Why does the universe follow mathematical laws at all? Why is mathematics so effective at describing reality? This is what physicist Eugene Wigner called the unreasonable effectiveness of mathematics. Tegmark's answer is radical but elegant. Mathematics is effective at describing reality because reality is mathematics. The universe is not a physical thing that happens to follow mathematical rules. The universe is a mathematical structure, and what we perceive as physical reality is the internal experience of being part of that structure. Our particles are mathematical objects. Our forces are mathematical relationships. Our space and time are mathematical dimensions. There is no distinction between the map and the territory. The map is the territory. If this is true, then every self-consistent mathematical structure is a universe. There is a universe described by the equations of classical mechanics, a universe described by the equations of quantum field theory, a universe described by the equations of string theory, a universe described by every possible set of consistent mathematical axioms, and beyond those there are universes described by mathematical structures that humans have never conceived of, structures in branches of mathematics that we have not yet developed, structures that may require types of logic that human minds are not capable of. This is what Tegmark calls the Level 4 multiverse, the ensemble of all mathematical structures, each one a complete physical universe. Beyond the edge of our universe lies not just more space or other bubbles or higher dimensions, but the entirety of mathematical reality. Every universe that could possibly exist, defined by every possible set of consistent equations, exists. The set of all possible realities. The ultimate multiverse. The ultimate answer to the question of what lies beyond. Now, this is a deeply controversial idea, and many physicists and philosophers have criticized it. How can a mathematical structure be physical? What does it mean for an equation to exist physically? Is there really no difference between a universe and its mathematical description? These are difficult questions, and I do not think anyone has fully answered them. But the mathematical universe hypothesis has a certain logical inevitability to it. If the universe is truly mathematical, and if mathematical existence is equivalent to physical existence, then the multiverse of all mathematical structures follows as a logical necessity. And the question of what lies beyond the edge becomes the question of what other mathematical structures are possible, a question that mathematics itself can answer. So, those are our 6 possibilities. Beyond the edge of the universe might lie more of the same universe, stretching perhaps to infinity. It might lie true nothingness, the absence of space and time and everything. It might lie other bubble universes, spawned by eternal inflation, each with its own physics. It might lie higher dimensional space, with other brains floating nearby. It might lie the computational substrate of a simulation, or it might lie the realm of all possible mathematics, the ultimate ensemble of all possible realities. Each of these possibilities is supported by serious physics and serious mathematics. Each has its proponents and its critics. And the honest truth, the deeply humbling truth, is that we do not know which one is correct. We may never know. But the fact that we can even ask the question, that we can formulate these possibilities, that we can reason about them with mathematics and test them against observations, that itself is a kind of miracle. But we are not done yet, because there is another dimension to the question of what lies beyond the edge, and it is the dimension of time. We have been talking about what lies beyond the edge in space, but what lies beyond the edge in time? What is the ultimate fate of the universe? And how does that fate connect to the question of boundaries and edges? The fate of the universe depends on the behavior of dark energy, that mysterious force driving the accelerating expansion. And dark energy's behavior over the coming billions and trillions and googles of years will determine whether the universe ends in ice or fire, in a whimper or a scream, in eternal darkness or a new beginning. The first and most likely scenario, based on our current understanding, is called the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to drive the expansion of the universe at an accelerating rate, but the acceleration is steady, not increasing. The universe continues to expand forever, and as it expands, it cools. Galaxies drift apart from each other, becoming isolated islands of light in an ever-growing sea of darkness. Within each galaxy, stars continue to burn, fusing hydrogen into helium, helium into carbon, carbon into heavier elements. But the fuel is not infinite. Eventually, all the hydrogen gas in the galaxy is used up, and no new stars can form. The existing stars burn out, one by one. The small dim red dwarf stars, which burn their fuel the most slowly, will be the last to go. They can burn for trillions of years, far longer than the current age of the universe, but even they will eventually exhaust their fuel and fade into cold, dark embers called black dwarfs. The universe at this stage, perhaps 100 trillion years from now, will be a dark, cold place. No stars will shine. The only light will come from the occasional collision of dead stars or the rare formation of a new star from stray gas. But these events will become less and less frequent as the last traces of gas are used up. But the story does not end there. It gets worse. Much worse. After the stars are gone, the remaining structures, the dead stars, the planets, the black holes, will begin to disintegrate. Protons and neutrons, the building blocks of atoms, are predicted by many theories to be unstable, with a half-life of perhaps 10 to the power of 40 years or more. Over unimaginable eons, longer than any number you have ever encountered, the atoms that make up every planet, every dead star, every grain of dust will decay into subatomic particles, into positrons and neutrinos and photons. Solid matter will dissolve into a thin haze of elementary particles, drifting through an expanding void. And then, even the black holes will die. Stephen Hawking showed in 1974 that black holes are not truly black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near their event horizons. This radiation carries energy away from the black hole, and over time, the black hole slowly evaporates. For a stellar mass black hole, this process takes about 10 to the power of 67 years. For a supermassive black hole like the one at the center of the Milky Way, it takes about 10 to the power of 100 years. That is a 1 followed by 100 zeros. A Google years. After all the black holes have evaporated, the universe will contain nothing but a thin, cooling soup of photons, neutrinos, electrons, and positrons, spreading out through an ever-expanding void. The temperature of the universe will approach, but never quite reach, absolute zero. The entropy of the universe will approach, but never quite reach, its maximum value. And in this state, the universe will exist for an eternity, not just a long time. An actual eternity, forever. A cold, dark, empty, changeless void, stretching without limit in every direction and every moment. Forever. This is the heat death of the universe. It is the most probable ending of the story, and it is, in my opinion, the loneliest, saddest, most hauntingly beautiful fate imaginable. Because it means that everything we know, everything we love, everything we have ever created or experienced or dreamed, exists in a tiny, fleeting window of time in a cosmos that will spend almost all of its existence in cold, silent darkness. We live in the springtime of the universe, and spring will not last. But it is spring now, and that matters. That matters more than I can express. The second scenario for the fate of the universe is more violent and more dramatic. It is called the Big Rip. This scenario occurs if dark energy is not just constant, but actually grows stronger over time. There is a hypothetical form of dark energy called phantom energy, which has a property that causes it to become more and more powerful as the universe expands. If phantom energy is real, then the expansion of the universe will not just accelerate. It will accelerate at an ever-increasing rate, eventually tearing apart everything in the cosmos. Here is how it would unfold. First, billions of years from now, the expansion becomes so rapid that galaxy clusters are pulled apart. Individual galaxies are flung away from each other faster than light. Then, the expansion becomes so powerful that it overwhelms the gravitational binding of individual galaxies. Stars are flung out of their galaxies, scattered into the void. Then, solar systems are disrupted. Planets are torn from their orbits around their stars. Then, the expansion becomes so extreme that it overwhelms the electromagnetic and nuclear forces that hold matter together. Planets are ripped apart. Mountains crumble. Rocks shatter. The molecules in your body are torn apart. Atoms are ripped into subatomic particles. Protons and neutrons are torn into quarks. And finally, space-time itself is ripped apart, producing a singularity not unlike the one at the Big Bang, but in reverse. Everything is shredded into nothingness. Calculations suggest that if phantom energy exists and the Big Rip occurs, it could happen about 22 billion years from now. The final moments would be dramatic and rapid. In the last year before the rip, the solar system would be unbound. In the last day, Earth would explode. In the last fraction of a second, atoms would be torn apart. And then, nothing. Or everything. The singularity at the end of the Big Rip might be a new beginning, just as the singularity of the Big Bang was. Or it might be the end of everything forever. We do not know. The Big Rip is less likely than the Big Freeze, based on current observations. Measurements of the expansion rate suggest that dark energy is probably constant, not growing. But we cannot rule out phantom energy entirely. Our measurements have a margin of error, and phantom energy lurks within that margin. It is a possibility that we cannot dismiss. The third scenario is the Big Crunch and its more hopeful cousin, the Big Bounce. In this scenario, the expansion of the universe eventually slows down and reverses. Dark energy somehow weakens or disappears, and gravity takes over, pulling everything back together. The expansion turns into contraction. Galaxies begin moving toward each other instead of away. The universe heats up as it compresses. Eventually, everything in the universe is compressed back into a single point. A singularity, just like the one at the beginning of the Big Bang, but in reverse. This is the Big Crunch. The universe ends in a fiery implosion, the mirror image of its explosive birth. But what happens at the crunch? Does the universe simply end? Or does the compression trigger a new Big Bang, a new explosion, a new expansion, a new universe? This is the Big Bounce, the idea that the Big Crunch is followed by a new Big Bang, and the universe is born again. In this model, the universe is cyclic, undergoing an eternal series of expansions and contractions, Big Bangs and Big Crunches, births and deaths and rebirths. There is no beginning and no end, just an endless oscillation, like a cosmic heartbeat. The cyclic model has a long history in both science and philosophy. Hindu cosmology, for example, speaks of an eternal cycle of creation and destruction, with the universe being created and destroyed by Brahma over and over again, each cycle lasting billions of years. Modern physicists have developed rigorous mathematical versions of the cyclic model. Roger Penrose, one of the greatest living physicists, has proposed a model called conformal cyclic cosmology, or CCC, in which the heat death of one universe is mathematically identical to the Big Bang of the next. In Penrose's model, when the universe reaches its final state of maximum entropy, a cold, empty void of photons and other massless particles, the distinction between large and small scales disappears, because without massive particles, there is no way to measure distance. The vast, empty universe becomes mathematically equivalent to a tiny, hot, dense point. The end is the beginning. The heat death is the Big Bang, and the cycle begins anew. Penrose has even claimed to have found evidence for this model in the cosmic microwave background radiation. He has identified what he calls Hawking points, which are small, warm circles in the CMB that he interprets as the remnants of black holes evaporating in the previous cycle of the universe. These black holes, he claims, left an imprint on the CMB that survived the transition from the previous universe to our own. This claim is highly controversial and is not accepted by most cosmologists. But it is a fascinating example of how the question of the universe's fate is connected to the question of its origins, and both are connected to the question of what lies beyond. The fourth, and perhaps most terrifying scenario for the fate of the universe is vacuum decay, sometimes called the Big Slurp. This scenario is based on the physics of the Higgs field, the quantum field that gives particles their mass. The discovery of the Higgs boson at the Large Hadron Collider in 2012, with a mass of about 125 giga-electron volts, had an unexpected and unsettling implication. The mass of the Higgs boson suggests that the Higgs field might not be in its most stable state. It might be in what physicists call a false vacuum, a state that appears stable but is actually only metastable, like a ball perched on a ledge halfway up a hill. The ball is at rest, it seems stable, but it is not at the bottom of the hill. A sufficiently large disturbance could knock it off the ledge, and it would roll down to the true bottom. Similarly, the Higgs field might be in a false vacuum, a local minimum of energy that is not the global minimum. If the field were to tunnel to the true vacuum, the lower energy state, the results would be catastrophic. The transition from the false vacuum to the true vacuum would release an enormous amount of energy and fundamentally change the properties of the universe. The masses of particles would change. The strengths of forces would change. Chemistry as we know it would cease to exist. Atoms, as we know them, might not be stable. The transition would begin at a random point in space, a quantum fluctuation that nucleates a bubble of true vacuum. This bubble would expand at the speed of light, consuming everything in its path. Inside the bubble, the laws of physics would be different. Life would be impossible, and we would have no warning. The bubble would arrive at the speed of light, so we could not see it coming. One moment everything is normal. The next moment, you and everything around you is replaced by a fundamentally different kind of space with fundamentally different physics. This is genuinely terrifying. But there is some comfort to be had. First, if the universe has existed for 13.8 billion years in the false vacuum state without decaying, the probability of decay in any given moment must be extremely low. The half-life of the false vacuum might be vastly longer than the current age of the universe, perhaps 10 to the power of 100 years or more. We might have a very, very long time before vacuum decay occurs, if it occurs at all. Second, some physicists argue that the universe might actually be in the true vacuum, or that the calculation is too uncertain to draw firm conclusions. The exact stability of the Higgs field depends on the precise mass of the top quark and other parameters that have not been measured with sufficient accuracy, but the possibility remains. Somewhere, possibly far beyond the edge of our observable universe, a bubble of true vacuum might already be forming. It might have formed billions of years ago. It might be racing toward us right now at the speed of light. we would never know until it arrived. And then we would not know anything at all. These four scenarios, the big freeze, the big rip, the big crunch and bounce, and vacuum decay, represent the four ways the universe might end. And each one connects to the question of what lies beyond the edge. In the big freeze, the edge of the universe in time is an eternity of cold, dark emptiness. In the big rip, the edge is a cosmic catastrophe that tears apart space itself. In the big crunch and bounce, the edge is a new beginning, a new universe born from the death of the old. And in vacuum decay, the edge is a wall of destruction, a phase transition that rewrites the laws of physics. Now, let us shift gears and talk about some of the philosophical implications of everything we have discussed, because the question of what lies beyond the edge is not just a physics question. It is a question that touches on the deepest issues in philosophy, the nature of existence, the limits of knowledge, the meaning of consciousness, and the relationship between mathematics and reality. One of the most profound philosophical questions raised by our exploration is this: why is there something rather than nothing? This is a question that has been asked by philosophers for centuries, most famously by Gottfried Wilhelm Leibniz, who called it the first question which should rightly be asked. Why does the universe exist at all? Why is there space and time and matter and energy? Why is there not simply nothing? This question is closely connected to the question of what lies beyond the edge. If the universe has an edge, and beyond that edge is nothing, then the question becomes, why is there a universe surrounded by nothing? What caused the universe to pop into existence from the void? On the other hand, if there is no nothing, if every possible universe exists, if the multiverse is real and encompasses all mathematical structures, then the question becomes, why is mathematical existence the same as physical existence? Why does a set of equations produce a real, tangible universe? Lawrence Krauss, in his book A Universe from Nothing, argued that the universe could have arisen from a quantum fluctuation in the vacuum. In quantum mechanics, the vacuum is not truly empty. It is a seething foam of virtual particles constantly popping into and out of existence. Krauss suggested that the entire universe could be one such fluctuation, a vast quantum event that created space and time and matter from the energy of the quantum vacuum. In this view, the universe literally came from nothing, or at least from what physicists call nothing, the quantum vacuum. But critics, including philosopher David Albert, pointed out that the quantum vacuum is not nothing. It is a quantum field, governed by the laws of quantum mechanics, existing in space-time. It is a very specific something. True philosophical nothing would be the absence of everything. No quantum fields, no laws of physics, no space-time, no mathematics, no logic. True nothing is the absence of the potential for anything to exist, and from true nothing, it seems logically impossible for something to arise. So, either the universe arose from something, in which case we need to explain where that something came from, leading to an infinite regress, or the universe simply exists as a brute fact, with no reason or cause, which is deeply unsatisfying philosophically. Or there is some deeper principle, some meta-law, some logical necessity that ensures that something exists. Some philosophers have argued that nothingness is unstable, that the default state of reality is existence rather than non-existence. Others have argued that existence is a mathematical tautology, that the set of all possible mathematical structures necessarily includes structures complex enough to contain observers, and we are those observers. These are deep waters, and I do not think anyone has a fully satisfying answer. But they are intimately connected to our question. What lies beyond the edge of the universe might be nothing, but nothing might be impossible. And if nothing is impossible, then something must exist. And if something must exist, then the universe, or the multiverse, or the mathematical structure that contains all possible realities, exists not by chance but by necessity. It exists because it cannot not exist. Another fascinating philosophical issue raised by our exploration is the anthropic principle. The anthropic principle observes that the universe appears to be remarkably fine-tuned for the existence of life, particularly conscious life. The fundamental constants of nature, the strengths of the four forces, the masses of particles, the amount of dark energy, the number of spatial dimensions, seem to be set to values that are just right for life to exist. If any of these values were slightly different, the universe would be sterile. Let me give you some examples. The strong nuclear force which holds atomic nuclei together has a specific strength. If it were about 5% stronger, hydrogen would be unstable, and the universe would contain no hydrogen. Without hydrogen, there would be no water and no hydrogen-based chemistry. Life, as we know it, would be impossible. If the strong force were about 5% weaker, deuterium, an isotope of hydrogen, would be unstable, and the nuclear reactions that power stars would not work. Stars would not shine, and the elements necessary for life would never be produced. The electromagnetic force has a specific strength, characterized by the fine structure constant, which has a value of approximately 1/137. If this value were significantly different, atoms would not be stable, chemistry would not work, and the complex molecules necessary for life could not form. The cosmological constant, which characterizes the density of dark energy, has a measured value of approximately 10 to the power of -122 in natural units. This is an astonishingly small number. If it were much larger, the expansion of the universe would be so rapid that galaxies, stars, and planets could never form. If it were large and negative, the universe would have collapsed long ago. The fact that it has the incredibly precise value it does, a value that allows structure to form but does not cause the universe to collapse, seems like an astounding coincidence. The odds of getting this value by chance have been estimated at 1 in 10 to the power of 120. That is a number so absurdly small that it defies comprehension. The anthropic principle offers two interpretations of this fine-tuning. The weak anthropic principle simply observes that we can only exist in a universe that permits our existence. We should not be surprised to find that the universe's constants are compatible with life, because if they were not, we would not be here to observe them. This is a tautology, but it is an important one. It reminds us that our observations are biased by the fact that we exist. The strong anthropic principle goes further, suggesting that the universe must have properties that permit the existence of observers. This is a more controversial claim, and it borders on teleology, the idea that the universe has a purpose or goal. Most scientists are uncomfortable with the strong anthropic principle because it seems to invoke design or intentionality, which are not scientific concepts. But the multiverse provides a third interpretation. If there are an enormous number of universes, each with different values of the fundamental constants, then most of those universes will be sterile. They will not have the right conditions for life. But a few of them, by pure chance, will have constants that are just right, and conscious beings will only exist in those few universes. So the fact that we observe a universe that is fine-tuned for life is not a miracle or a coincidence. It is a selection effect. We observe a fine-tuned universe because we can only exist in a fine-tuned universe. The multiverse provides the ensemble of universes, and the anthropic principle provides the selection criterion. This is one of the strongest arguments in favor of the multiverse, because it provides a natural, non-miraculous explanation for the apparent fine-tuning of the universe. Without the multiverse, the fine-tuning seems like an extraordinary coincidence that cries out for explanation. With the multiverse, it is simply a consequence of the fact that we exist in one of the rare universes that permits existence. But not everyone is satisfied with this argument. Some critics argue that invoking an unobservable multiverse to explain the fine-tuning is no better than invoking an unobservable God. Both are untestable. Both are invoked to explain something that seems improbable. Both could be dismissed by Occam's razor, which tells us not to multiply entities beyond necessity. Whether the multiverse is a scientific explanation or a metaphysical one is a question that the physics community is still debating. Let me now take you to what I consider one of the most profound aspects of our question: the limits of human knowledge. Can we ever know what lies beyond the edge of the universe? Or is this a question that is fundamentally unanswerable? There are several reasons to think that the answer might be unknowable. The first is practical: the cosmic horizon. As we discussed, the expansion of the universe limits how far we can see. Light from regions beyond the observable universe has not had time to reach us, and because of the accelerating expansion, much of it never will. We are trapped inside a bubble of visibility, and the universe beyond that bubble is inaccessible to our instruments. We cannot send probes there. We cannot receive signals from there. We cannot observe it in any way. We are, in a very real sense, prisoners of the speed of light. The second reason is more fundamental: the limits of science itself. Science operates by formulating hypotheses and testing them against observations. But if other universes, or the region beyond our cosmic horizon, or the higher dimensional bulk, can never be observed, even in principle, then hypotheses about them can never be tested. And a hypothesis that cannot be tested is not a scientific hypothesis. It is a philosophical speculation. This does not mean it is wrong. It does not mean it is meaningless. But it does mean that science alone may not be able to answer the question. The third reason is the deepest: the limits of human cognition. Our brains are products of evolution. They were shaped by natural selection to solve the problems of survival on the African savanna, finding food, avoiding predators, navigating social relationships, throwing spears, recognizing faces. Our brains were not designed to understand the nature of reality at its deepest level. The fact that we can understand as much as we do, that we can comprehend quantum mechanics and general relativity and cosmology, is remarkable and perhaps accidental. But there may be aspects of reality that are simply beyond the capacity of the human mind to grasp, just as calculus is beyond the capacity of a dog's mind, and algebra is beyond the capacity of a goldfish's mind. Mathematician Kurt Gödel showed in 1931 that any sufficiently powerful mathematical system contains true statements that cannot be proven within that system. This is Gödel's incompleteness theorem, and it places a fundamental limit on what mathematics can achieve. Could there be a similar limit on what physics can achieve? Could there be truths about the universe that are real but unprovable? Questions about reality that have definite answers but that no experiment, no theory, no amount of reasoning can ever determine. Some physicists and philosophers believe so. They argue that the question of what lies beyond the edge of the universe may be one of these fundamentally unanswerable questions. It has a definite answer. There is something beyond the edge, or there is not, but we may never be able to determine what that answer is. It is a truth that exists, but that is forever beyond our reach. Others are more optimistic. They point to the history of science, which is a history of breaking through barriers that were thought to be impassable. People once thought we could never know what stars are made of, until spectroscopy revealed their compositions. People once thought we could never know the age of the universe, until the cosmic microwave background radiation gave us a precise measurement. People once thought we could never detect gravitational waves, until LIGO succeeded in 2015. Again and again, the limits of the possible have been pushed back. Maybe the question of what lies beyond the edge is just the latest barrier, one that future generations will find a way to break through. I find both perspectives compelling. The humility of acknowledging our limitations is important, but so is the audacity of pushing beyond them. And perhaps the most important thing is the asking itself. The question matters, even if the answer is unknowable. The journey matters, even if the destination is unreachable. The search for truth is valuable in itself, regardless of whether we ever arrive at the final truth. Now, let me share with you what some of the greatest scientific minds of our time think about this question. Because while we have been exploring theories and possibilities, it is worth hearing from the people who have devoted their lives to studying the cosmos, the people who know more about the universe than anyone else alive. Stephen Hawking, perhaps the most famous physicist of the modern era, believed that the question of what lies beyond the edge of the universe is, in a sense, a meaningless question. His no-boundary proposal, developed with James Hartley, suggested that the universe is self-contained, with no edges in either space or time. In Hawking's view, asking what is beyond the edge of the universe is like asking what is south of the South Pole. The question presupposes a direction that simply does not exist. Hawking's universe is a closed, finite, self-contained reality, with no outside and no before. It simply is. Hawking once said, "So long as the universe had a beginning, we could suppose it had a creator." But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place, then, for a creator? Whether or not you agree with Hawking's philosophical conclusions, his no-boundary proposal is a mathematically rigorous attempt to answer our question. And it says, there is no beyond because there is no edge. Alan Guth, the physicist who first proposed cosmic inflation, believes strongly in the multiverse. He sees it as an almost inevitable consequence of inflation theory. If inflation happened once, in the early moments of our universe, it almost certainly happened many times, creating many universes. Guth has said, "The multiverse is the prediction of the best theory we have for what happened at the beginning of the universe. You might not like it, but there's no reason to reject it just because it conflicts with your intuition." Guth's view is that beyond the edge of our universe lies an infinite, ever-inflating space dotted with an infinite number of bubble universes, each one a separate reality. Andre Linde, who independently developed and extended inflation theory, goes even further. Linde describes the multiverse as a self-reproducing, eternally inflating fractal. In his view, the universe is constantly creating new regions of space, new pocket universes, in an endless, self-sustaining process. The universe is not dying, Linde has said. The universe is immortal, it's self-reproducing. New universes are being born all the time. Linde sees the multiverse not as a speculative possibility but as a direct and unavoidable consequence of the physics of inflation. Roger Penrose, one of the most brilliant and original thinkers in modern physics, takes a different view. Penrose is skeptical of the inflationary multiverse and has proposed his own alternative: conformal cyclic cosmology. In Penrose's model, the universe is cyclic, with each cycle ending in a heat death that seamlessly transitions into the Big Bang of the next cycle. Beyond the edge of our universe, in Penrose's view, is the remnant of the previous universe, the universe that came before ours, whose dying breaths gave birth to our cosmic dawn. Penrose has said that he has found evidence for this in the form of Hawking points in the cosmic microwave background, though this claim remains controversial. Max Tegmark, the MIT physicist who proposed the mathematical universe hypothesis, has the most expansive view of all. For Tegmark, beyond the edge lies not just more universe or other universes, but the entirety of mathematical reality. Every possible universe that can be described by a self-consistent mathematical structure exists. Our universe is one structure among infinitely many. Tegmark has classified the multiverse into 4 levels. Level 1, the regions beyond our cosmic horizon that look like our universe. Level 2, the bubble universes with different physics, produced by eternal inflation. Level 3, the branches of the quantum multiverse, produced by the many worlds interpretation of quantum mechanics. And Level 4, the ensemble of all mathematical structures. Each level is more radical and more encompassing than the last. In Tegmark's view, the answer to what lies beyond the edge is everything. Everything that can exist does exist. Sean Carroll, a theoretical physicist and cosmologist at Johns Hopkins University, is a proponent of the many worlds interpretation of quantum mechanics. In this interpretation, first proposed by Hugh Everett in 1957, every time a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. If you measure an electron's spin and it can be either up or down, the universe splits into 2, one where the spin is up and one where the spin is down. Both branches are equally real. Both continue to exist, and the branching happens constantly, trillions upon trillions of times per second, every time a quantum event occurs anywhere in the universe. The result is an unimaginably vast tree of branching universes, each one slightly different from the others. Carroll has said, "The many worlds interpretation is the simplest, most elegant interpretation of quantum mechanics. It takes the equations seriously and doesn't add any extra assumptions." In Carroll's view, beyond the edge of our universe, in a sense that is orthogonal to the spatial dimensions, are the other branches of the quantum multiverse, the other versions of our universe that branched off at every quantum event since the Big Bang. Leonard Susskind, a theoretical physicist at Stanford University and one of the founders of string theory, emphasizes the cosmic landscape. In Susskind's view, string theory predicts an enormous number of possible vacuum states, each corresponding to a different set of physical laws. The number of possible vacua is estimated at 10 to the power of 500. Each vacuum might be realized in some region of the multiverse. Susskind has said, "The landscape of string theory is our best candidate for explaining why the universe has the properties it does. We live in a particular valley of the landscape, not because it's special, but because it's one of the vast number of valleys that supports life." Lee Smolin, a theoretical physicist at the Perimeter Institute in Canada, has proposed a radically different view called cosmological natural selection. Smolin suggests that universes reproduce through black holes. When a black hole forms, it creates a new baby universe inside it, a new region of space-time with slightly different physical constants. Universes that are good at producing black holes will produce many offspring, while universes that are bad at producing black holes will produce few. Over many generations of universe reproduction, the physical constants will evolve toward values that maximize black hole production. And, by a remarkable coincidence, the values that maximize black hole production are also values that permit the existence of complex chemistry and life. Smolin's model is unique among multiverse theories because it makes attestable predictions. It predicts that the physical constants of our universe should be near a local maximum of black hole production, meaning that small changes to any constant should decrease the rate of black hole formation. Some tests of this prediction have been performed with mixed results. These are some of the greatest minds of our era, and they do not agree. They cannot even agree on whether the question of what lies beyond the edge is answerable. But what they do agree on is that the question is important, that it is worth asking, and that the pursuit of the answer is one of the noblest endeavors of the human mind. Now, before we wrap up, I want to take you into the darkest corners of this question, the most terrifying possibilities, the ideas that keep cosmologists awake at night. Because if we are going to explore what lies beyond the edge, we need to confront not just the beautiful possibilities, but the disturbing ones too. The first terrifying possibility is the Boltzmann brain. This idea comes from the work of the 19th century physicist Ludwig Boltzmann, who was one of the founders of statistical mechanics. Boltzmann showed that the entropy of a system, its disorder, tends to increase over time. But he also showed that, given enough time, random fluctuations could temporarily decrease entropy, creating pockets of order in an otherwise disordered system. In the context of the universe, this means that in the far, far future, when the universe has reached a state of maximum entropy, random quantum fluctuations could occasionally create structures of any complexity, including brains. Not biological brains that evolved over billions of years, but spontaneous brains that pop into existence fully formed, complete with memories and experiences created by random chance. These are called Boltzmann brains. The problem with Boltzmann brains is this. In an infinite universe that exists for an infinite amount of time, the number of Boltzmann brains produced by random fluctuations vastly outnumbers the number of biological brains produced by evolution. This means that, statistically speaking, you are far more likely to be a Boltzmann brain than a biological brain. You are far more likely to be a random fluctuation in a dead, empty universe than a real person on a real planet in a living universe. Your memories of your life, your experience of reading this right now, are far more likely to be false memories created by a random quantum event than genuine memories of real experiences. This is deeply unsettling, and it is not just a thought experiment. It is a genuine problem in cosmology. Any theory that predicts the universe will exist for an infinite amount of time must grapple with the Boltzmann brain problem. If the future is infinite, then Boltzmann brains will eventually vastly outnumber ordinary observers, and the theory's predictions become dominated by these random fluctuations, rather than by the orderly, structured observations that we actually make. This is sometimes called the measure problem in cosmology, and it is one of the deepest unsolved problems in the field. Some physicists have argued that the Boltzmann brain problem is a reason to prefer cosmological models in which the universe does not last forever. Models that avoid an infinite future, and thus avoid the production of an infinite number of Boltzmann brains. Others have argued that the problem can be solved by choosing the right way to count observers in an infinite multiverse. But no consensus has been reached. The thought that you might be a Boltzmann brain, a random fluctuation in an empty void, with false memories and a false experience of reality, is one of the most existentially disturbing ideas in all of science. And it is directly connected to the question of what lies beyond the edge. If you are a Boltzmann brain, then beyond the edge of your experience is not a vast cosmos full of galaxies and stars. It is a cold, dead, empty void, and you are a momentary spark of consciousness in an eternity of nothing, destined to dissolve back into the void a moment from now. Your entire universe, your entire life, your entire experience is a brief, meaningless hallucination in an ocean of entropy. Of course, most physicists do not believe we are Boltzmann brains. But the fact that the possibility must be taken seriously, that it follows logically from well-established physics, is a reminder of how strange and unsettling the universe can be when we push our questions to their logical extremes. The second terrifying possibility is that our universe might be the inside of a black hole. This might sound like science fiction, but it is a serious proposal that has been explored by several physicists, including Lee Smolin and Nikodem Poplawski. The idea is based on the observation that the Big Bang singularity, the point of infinite density from which our universe emerged, has a striking mathematical resemblance to the singularity at the center of a black hole. In general relativity, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where the density of matter becomes infinite, and the laws of physics as we know them break down. No one knows what actually happens at a singularity, because our physics is not equipped to describe it. General relativity predicts infinite density and infinite curvature, which are almost certainly unphysical. Something else must happen. Something that requires a theory of quantum gravity to describe. Poplawski and others have proposed that what happens at the singularity is not a point of infinite density, but a bounce, where matter that falls into the black hole rebounds and expands outward, creating a new region of space-time. This new region of space-time is causally disconnected from the exterior of the black hole. It is a separate universe inside the black hole that appears to its inhabitants as an expanding cosmos born from a singularity. In other words, our Big Bang might have been a bounce inside a black hole in a parent universe. If this is correct, then beyond the edge of our universe lies the interior of a black hole, and beyond that, the parent universe in which the black hole formed. And the parent universe might itself be inside a black hole in a grandparent universe, and so on. The multiverse, in this model, is a vast network of black holes, each containing a universe. Each universe containing black holes that contain further universes, stretching up and down through an infinite hierarchy of realities. This model has a beautiful self-similar structure, like a fractal. And it connects to Lee Smolin's cosmological natural selection. Universes that produce many black holes also produce many baby universes, leading to a kind of cosmic evolution in which the physical constants evolve toward values that favor black hole production. The third terrifying possibility is connected to the vacuum decay scenario we discussed earlier. The idea that the Higgs field is in a false vacuum, that a bubble of true vacuum could nucleate at any moment and expand at the speed of light, destroying everything in its path. What makes this terrifying is not just the destruction, but the total lack of warning. The bubble travels at the speed of light, which means you cannot see it coming. There is no signal, no alarm, no time to prepare. One moment, you exist. The next moment, you do not. And it could happen at any time. It could be happening right now, somewhere beyond the edge of the observable universe. A bubble of true vacuum expanding toward us at the speed of light. Already en route, already unstoppable, already inevitable. And we will never know until it arrives.